Hello everyone and welcome back to our course on machine learning. Today we begin one of the most essential topics in modern artificial intelligence that is called as reinforcement learning, or RL in short. Reinforcement learning is fundamentally different from the supervised and unsupervised paradigms we studied earlier. Instead of learning from statistic data sets, reinforcement learning focuses on learning from interaction. We have some agents. Agents continuously engage with an environment. They take action, they observe the consequences, and gradually they improve their behaviors. In this lecture, I'll guide you through the conceptual foundations, mathematical formulation, and algorithm mechanism that allow machines to learn optimal decision-making strategies over time. Reinforcement learning is about taking suitable action to maximize reward in a particular situation. So in this lecture, we are going to learn the basic principle of reinforcement learning. We will study by defining exactly what is reinforcement learning and how it fits into the broader machine learning landscape. We introduce the core framework involving agents, environments, and rewards. Then we will formalize this mathematically using Markov Decision Process. Finally, we will look at the fundamental algorithms that are used to solve these problems, like value iteration and policy iteration. So the main difference between reinforcement learning and two previous branches, supervised learning and unsupervised learning, is here. In case of supervised learning and unsupervised learning, we have data. For supervised learning, we use labeled data, typically labeled by an external supervisor, like subject matter expert or an algorithm or program. The data set is split into training and test data set for training and then validating the model. The supervised model is then used to generate prediction on previously unseen unlabeled data that belongs to the category of data the model was trained on. Then we have unsupervised learning. Unsupervised learning is learning by reasoning to identify hidden patterns in an unlabeled dataset. They have no supervision like the supervised learning algorithm. That's why we call them unsupervised learning. Then we have reinforcement learning. The goal of reinforcement learning is for the agent to learn to make sequential decisions in an uncertain environment. How? By mapping the different environment states to actions, and the goal is maximize long-term rewards. Reinforcement learning is unique because the goal is not merely to predict, but we want to determine which action produce desirable outcome. So what is reinforcement learning? At its core, it's learning by interacting with an environment. We have some agents. Agent takes action and receive feedback in the form of rewards or penalties. If it's a good action, it will receive reward. If it's a bad action, it will receive penalty. Reinforcement learning is different from unsupervised learning and supervised learning. Because here we don't have data, the agent must discover which action yields the most reward through the trial and error, try and fail. So in reinforcement learning, we mainly try to train agents. Our agents learn how to behave in an environment. How? By taking proper action. Then they observe the results. Agent can be a piece of code, it can be an algorithm, it can be a player, it can be a robot, it can be a car. So once again, we have agents. An agent operates in an environment by performing action and observing results. The agent perceives a state, selects an action, receives a reward, and transits to a new state, and continues this loop again and again. So the objective is to discover behavior that maximizes cumulative long-term reward, not just immediate payoff. So what makes the reinforcement learning unique? First, there is no supervisor, just a reward signal that tells the agent how good or bad is an action, but not necessarily what the best action would have been. Second, feedback is delayed. An action taken now might not yield a reward until many steps later. Third, time matters here. This is a sequential process, and crucially, the agent's action affects the subsequent data it sees. So the agent does not have any information about the environment. We don't have any training data set. The agent learns based on experience. What is the input here? The input is an initial state from which the agent will start. Then we have the training process. The training is based upon the input that we have. The model will return a state, and the user will decide to reward or punish the model based on its output. So what are the outputs? There are many possible outputs, as there are a variety of solutions to a particular problem. The agent receives rewards by doing the right action and receive penalty or negative rewards by doing wrong action. The best solution is decided based on the maximum reward. Finally, it will finish it with some outcome, either goal or fail. To place it in context, let's recall the main class of machine learning once again. Supervised learning used labeled data. We know the correct output. Unsupervised learning finds pattern structure in unlabeled data. Then reinforcement learning is distinct. It's about decision-making in dynamic environments in order to maximize a cumulative reward over time. So reinforcement learning differs from supervised learning in a way that in supervised learning, the training data set has the answer key with it. So the model is trained with the correct answer itself. However, in case of reinforcement learning, we don't have answer, but the reinforcement learning agent decides what to do to perform a given task. In the absence of training dataset, it is bound to learn from experience in reinforcement learning. Before continuing, I like to talk about this quote from George Bernard Shaw. He says, "We human beings learn from experience that men never learn anything from experience." This quote offers a cynical but yet insightful contrast to the core premise of reinforcement learning. While Shaw highlights humanity's recurring failures to internalize lessons due to complex motivation and biases, an RL agent is precisely designed to overcome this problem. How? By acting as a rational and also a reward maximizing entity with a clear objective. Reinforcement learning algorithms systematically adjust behavior based on environment feedback. It means it must learn from experience if the reward function is well defined and sufficient exploration occurs. So reinforcement learning includes agent and environment. The agent takes some action based on the observation. In every step, the agent updates its knowledge and decides the next action to perform. The loop continues till the agent reaches a terminal state, and in here, the agent completes the assigned task. By successfully completing the process, the agent receives rewards. So the reinforcement learning loop is a continuous feedback cycle. The agent observes the current state. The agent takes an action based on its current knowledge and policy. The agent receives a reward or penalty based on the action. Then it transitions to a new state, and then it updates its knowledge or value estimate. This cycle continues until the agent reaches somewhere to stop. That is called as terminal state. Through repeated iterations, the agent gradually improves its policy. Games provide ideal reinforcement. Think of chess, Go, Atari, or even modern RL-driven video games. Games have clear states. They have well-defined action, and also they have explicit reward structure and terminal outcome. Games also allow repeat simulation, which is why RL had breakthroughs in gaming environment. So in here, we have some agent and environment. Then the agent collects a state at S0 from the environment. Then based on the state S0, the agent takes an action, right? At the beginning, it will be random because the agent does not have any experience. Then from S0, by taking A0, it will be moved. It will be transit to S1, new state, right? Then by taking that action, the agent now gets a R1 as reward, right? Then the RL loop goes until the agent is dead or reach the destination. So we have states, we have actions, and we have rewards. Let's define these elements formally. The agent is the learner, and also it is the decision maker. Then we have environment. The environment is everything outside the agent that the agent interacts with the environment. The goal of the agent is to maximize the total reward that it receives over the long run. Beside the agent and environment, we have three crucial concepts that we need to define. One is policy. The next one is reward signal and value function. What is policy? Policy, usually we denote it by pi. This is the agent behavior function. Policy is a mapping from state to action. Given the current state of the environment, the policy tells the agent what action to take next. Policy can be a simple lookup table, or it can be a complex neural network. That is called as deep reinforcement learning. So in this case, we can have deep learning plus reinforcement learning, which call it as DRL. So we can use a complex neural network for what? For if we have the current state of the environment, what action we should take, the agent should take, right, based on some neural network. Then we have reward signal. The reward signal defines the goal in an immediate sense. At each time step, the environment sends a signal number that is the reward to the agent. The agent's sole objective is to maximize the total amount of reward it receives. This is how we tell the agent what we want it to achieve, but not how to achieve it, right? So their goal is to maximize their reward. While rewards tell us what is good right now, we have something called as value function. Value function tells us what is good in the long run. The value of a state is the total amount of reward an agent can expect to accumulate starting from the initial state following its current policy thereafter. A state might yield a low immediate reward, but have a high value because it leads to a very good state later on. Sometimes we have also a model of the environment. This is something that mimics the behavior of the environment, and this allows the agent to predict the next state and reward given a current state and action. Models are used for planning, thinking ahead before acting. So this leads to a major distinction in reinforcement learning approach. We may have model-based models, we may have model-free reinforcement learning models. model-based methods use models and planning to decide on actions. On the other side, model-free methods are simpler. They learn purely by trial and error, and directly they learn policies or values without trying to predict environment dynamics. Then we have discount here. Discount is an action that redirects the agent to failure, and it must be avoided. So one of the biggest challenges in reinforcement learning is exploration and exploitation trade-off. To get a lot of rewards, the agent must exploit action it already knows work well. But to discover those actions in the first place, it must explore actions it has not tried before. So exploration, it means searching, right? Exploitation, it means utilization, right? So we have to make a balance between these two. By balancing these two competing objectives, we can have a better model, but it is really critical. Then we have something called as regret. Even if you learn the optimal policy, you still make mistakes along the way. Regret is the difference between your rewards and expected rewards. So we try to minimize regret, and minimizing regret needs learning to be optimal. So regret measures how much better we could have done by choosing the optimal action at each step. This regret is used to quantify the cost of suboptimal decision making. We must minimize regrets because RL agents often begin by exploring, making mistakes, and gradually reduce regret as they learn the optimal strategy. That's why minimizing regret is critical. Then we have reward maximization theory. A reinforcement learning must be trained in such a way that he takes the best action so that the reward is maximized. Then we have something called as discount factor or gamma. The smaller gamma, the larger discount values. So we may have from 0 to 1. If it is close to 0, it prevents the agent for more exploration in dangerous area. If it is close to 1, it encourages the agent to explore. So this is a trade-off between exploration and exploitation. Let me give you one example here. We have a fox here, and these are chicken, right? So these are meat, and the fox is very interested in eating chicken. If the agent move from here to here, it will be +1. If it comes to here 0, it will be here +1, right? If it comes to here no, 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 then here it will be +1. But there is one big problem here. The problem is if the fox moves to this one, it will be eaten by this tiger, right? So this one should be avoided. This is decided by the discount factor or gamma. So we have two types of reinforcement learning, positive and negative. Positive reinforcement learning strengthens behavior by giving rewards for desirable actions. On the other side, negative reinforcement learning discourages harmful or risky action through penalties, or we call them as negative outcome. In RL, both positive and negative types are useful for shaping the long-term behavior of the agent. For example, penalties can help to define minimum performance standards, while rewards can encourage goal-directed actions. Reinforcement learning is applicable everywhere. For example, we can employ reinforcement learning for optimizing chemical reaction process. We can use reinforcement learning for controlling video game characters or AI players. We can use it for handling robotic tasks in industrial environment. Reinforcement learning is applicable for autonomously navigating unmanned aerial vehicles. All these tasks, they require sequential decision-making under uncertainty, and that's why reinforcement learning is a natural fit for them. So, and many more applications here in logistic, gameplay, like Go, scheduling problems. RL excels when we must make many independent decisions, especially when outcome depends on previous action. Again, reinforcement learning can be used for aircraft control, it can be used for autonomous cars, it can be used for traffic light coordination. These are real-world systems where adaptive control, continuous learning, and dynamic decision-making are critical. The next topic that we need to study is MDP, Markov Decision Process. Markov Decision Process is the mathematical approach for mapping a solution in reinforcement learning. MDPs provide a formal structure for states, actions, transitions, and rewards. These MDPs help use mathematically analyze policies. We can analyze value function and optimal decision making. So MDP is a discrete time stochastic control process. MDPs are employed for non-deterministic search problems, and they are useful for studying optimization problems solved via dynamic programming and reinforcement learning. So here we follow a Markov property, that is, future is independent of past, giving the present. I will explain more later. First, we have to give a big thanks to Andrei Markov. Andrei Markov was a Russian mathematician at St. Petersburg University. His work on stochastic process laid the foundation for Markov chain and Markov process. His insights on memoryless transition from the theoretical basis of modern RL and probabilistic modeling are very helpful for us. What is Markov chain? A Markov chain is a stochastic model where the next state depends only on the current state, not on the history. This is called as Markov property. So we need to understand this Markov property because it helps us later in understanding the reinforcement learning in details. So It's a stochastic model, and it is a mathematical system that experiences transition from one state to another according to certain probabilities or rules. The probability of each event depends on the state attained in the previous event. For example, here we have this chain. We are in state A, right? If we take an action by 40% probability, we move to E state, right? So this is state A, this is state E. If the agent is in state A and it takes action A1, by probability of 40%, it will go to E, and by probability of 60%, it remains in the same state. If the agent is in state E and take an action like A2, by probability of 30%, it will remain in the same state. By probability of 70%, it will be in state A. This is called as Markov chain. Now, we formally characterize a Markov decision process. A Markov decision process essentially combines two ingredients. One is called a stochastic process, and another one is decision-making agent. The stochastic process describes how states evolve probabilistically. And then a decision-maker agent, these select actions that influence those transitions. The agent receives rewards as it progresses. Over time, the goal is to maximize cumulative reward. So Markov decision process unify randomness and decision-making in a principled structure. It gives us a mathematical grounded way to think about optimal behavior in uncertain environments. We may have positive rewards and negative rewards, as already I explained. Roughly speaking, a process satisfies the Markov decision property if one can make prediction for the future of the process based on solely on its present state, as well as one could knowing the process full history, so independently from such history that is conditional on the present state of the system. Its future and past states are totally independent. We call it as memorylessness, right? This is for Markov decision process. This is like search. Successor function only depends on current state. This is very similar to search problem. When solving a maze with food pellets, we stored which food pellets were eaten. So this Markov property is fundamental, and it simply says the outcome of an action depends only on the current state, not on the entire past history. Mathematically, we can show like this. If we say st plus 1 is s prime, then it depends on s was in st taking some action, right? St minus 1 and action minus 1 up to 0, right? Then here we say only this is the history, right? This is the history, right? But in Markov decision process, we say the probability of st plus 1 is equal to s prime is based on, you can say current action. So this is the future action, right? Future, this is current. The next state depends on the current state where we take this action, right? So it means we are in ST, we take action AT, and we move to ST plus 1, right? This is the meaning of Markov property. This assumption drastically simplifies the learning problem. Why? Because we don't need to track long sequence of past data. Instead, all relevant information is encapsulated in the present state. An MDP consists of several key components. We have T, we have S, we have action, we have probability of transition, and we have rewards, right? Where T is in T, S is in S, and A is in possible actions. What are the states? States are all possible configuration in which the agent can exist. So this is for states. Actions, all choices available to the agent at each state. For example, the fox could move backward, right, left, and forward, right? These are possible actions. Then we have a transition function, this one. This is a probability distribution describing where the agent lands after taking an action, right? We can have T as discrete, like finite or countably infinite set of states, or it can be finite, assume that no decision in taking in the final decision epoch. So if T is finite, we can have a finite horizon, like T is in 1 to up to n, and we may have infinite horizon, T is equal to 1, 2, 3, up to positive infinity. In here, we have a reward function. This is reward function. This is a kind of immediate numerical feedback for each transition. Also, we have policy, that is the strategy mapping state to action. So each of these components play a specific role in enabling optimal sequential decision making. So I already explained about the state, right? State, we have some state that when an agent takes an action, it moves from one state to another. AS is all possible actions, right? A set of possible actions for the agent. Then we have here PT. In one state, taking an action, we move to new state. What is the probability? That one, right? PT, new state, given S and A is the transition probability. This one specify how the state of the system change from one decision epoch to the next, right? Then we have reward function that give us rewards. For example, if the agent is here in the state T, in this state, if we take action number 1, By the probability of 80%, we will go to this state. By probability of 20%, we go to this state. If we take action number 2, by probability of 10%, we go to this state. By probability of 60%, go to this state. By probability of 30%, we go to this state. This is called as transition probability. And for each action, there is some reward, right? Moving from one state, by taking some action, there is some reward. It can be positive or negative. Let's see how an agent may choose an action based on value estimate. A decision rule essentially picks the action that maximizes the expected reward or value in the current state. So this decision rule tells the decision maker, the agent, how to choose the best action to be taken in a given decision epoch, right? We have a series of decisions. And for Markovian or deterministic decision rule, we have like delta T S to A. Then we have policy. I already explained about policy. Policy is a sequence of decision rules like delta 1, delta 2, up to delta 3 for every decision epoch. We may have a stationary policy, if the same decision rule is used in every decision epoch. So our goal here is to have a policy, the best policy, or you can say the optimal policy. Optimal policy which can help us to reach our goal. What is the goal in reinforcement learning? Maximize the total reward. A policy, as I say, defines how the agent behaves. A policy can be either deterministic or stochastic. In deterministic policy, we always choose a specific action in a given state. And in the case of stochastic policy, we choose actions according to a probability distribution. So in reinforcement learning, the ultimate goal is to find the optimal policy that we show by pi star, and this leads the highest cumulative reward over time. An optimal policy ensures that for every state, the chosen action yields the highest possible expected long-term return. Formally, we can define V star S, like this one. This is the optimal value of state S. Then the optimal policy select the action that aligns with this value. Once an optimal policy is found, the agent behavior becomes globally optimal across all possible situations. Next, we need to study Bellman function. The Bellman optimality equation is one of the most important equations in the context of reinforcement learning. So a Bellman equation, which has been named after Richard Ernest Bellman, this is a necessary condition for optimality associated with the mathematical optimization methods. We call them as dynamic programming. So we have this equation, and this is called as Bellman optimality equation. We want to finally maximize our reward. So VTSD is equal to AT in all possible AST. Find an action AD. Tell me which action maximizes this one, right? This total. So what action shall I take to maximize this one? What is this one? Two things are here. 1, 2. The first one is expected immediate rewards, right? Immediate reward in this period. And the next one is expected maximum total remaining rewards, right? So very simple. This function says, what action shall I take to maximize these two rewards? This is a recursive structure, and it tells us the value of a state is the reward from taking the best action plus the discounted value of the next state. This principle forms the foundation for value iteration and Q-learning that we will study later. Once again, about the Bellman optimality equation. This equation, we use it to find an action which results in maximizing the expected immediate reward plus the expected maximum total reward to go. The optimal action is the one with the highest expected future value. In reinforcement learning, action selection is always based on evaluating the long-term consequence of actions, not just immediate rewards. This long horizon reasoning is what makes reinforcement learning suitable for complex tasks like robotic and autonomous driving. So, objective here is to, based on the Bellman equation, select an action or action A2 that maximizes the expected reward, right? So, for example, we are here in S, we have two actions, A1 and action A2, right? If we take the action by probability of this S prime given S and A1, we will move to this state, and here is the reward. By this probability, I will come to this one, right? If I take action number 2, then by this probability, I will go to here, by this probability, I will go to here, by this probability, I will go to here, right? If I take action A1, the RTS and 1, this one, plus VT plus 1, S prime, multiply the probability of transition for VT plus 1, and that go to this one, multiply the probability of this one, right? So this is how we can calculate the total reward. And in the same way, we can calculate for these three possibilities that action A2 may help us to move, right? Then the action with the highest value will be selected among A1 and A2. We now move to grid world. This is a well-known example in reinforcement learning research. Grid world allows us to visualize state as grid cells, action as movements, and reward assigned to a specific location, and also transition influenced by noise. Suppose the agent is somewhere here in the maze, right? And if the agent takes an action to the north, then 80% of the time agent ends with going to the cell on the north if there is no wall, and 10% go to west and 10% go to the east. So the goal here is to maximize sum of rewards. So we have two kind of grid board: deterministic grid board and non-deterministic, or you can say stochastic grid board. In a deterministic grid board, every action leads to a predictable outcome, and in here transitions are consistent and also they are noise free. This is convenient for illustrating concepts, but real environments are almost never purely deterministic. In the case of deterministic, the agent knows exactly what will happen. However, in case of stochastic, the game must plan under uncertainty, no clear. So in this case, MDPs are essential because they explicitly model this uncertainty, and also those MDPs allows us to compute optimal strategy despite it. So once again, real-world environments are inherently noisy. Actions may not always lead to the intended result. So in order to model these uncertainties, we should go for MDPs, Markov Decision Process. Here is one example of racing. We have a robot car, and this robot car wants to travel far and quickly, right? So we have three states: cool, warm, and overheated, right? This is cool, this is warm, and this is overheated, right? Then we have two actions. The car can drive slow or fast, right? But if it goes faster, it gets double rewards. But how much fast it can go? Because there is a problem of overheating. If it's in start state and it goes slow, by probability of 100%, it will remain in the same state, which is cool. If it drives fast, by probability of 50%, it go to warm state. However, still there is a probability of 50% to stay in the cool state. If the car is in warm state and it go fast, 100% it will go to overheated. If the car is in warm state and if it drives slow, by probability of 50%, it go back to the cool state, and by probability of 50%, it remains in warm state. The question here is, what is the optimal policy in this example? So here we can see race search tree. If the car is in cool state, if it goes slow, it remains in here in the cool state. If it is in cool state, if it drives slow, still in cool state. If it drives fast, 50% remain in cool state, 50% it go to warm. Then if it drives fast, 50% it may remain in the cool state, 50% it go to warm. If it is here, again, same is here, then here. If it is in warm state and if it drives fast, 100% it will be overheated. And if it drives slow, 50% go back to the cool state and 50% it remains in the warm state. So the question here is, can we use Expectimax for MDP directly? What is the meaning of Expectimax algorithm? So far, we studied Markov decision process. A Markov decision process consists of a stochastic process and a decision maker that observes the process and select action that influence its development over time. The decision maker receives a series of rewards. It can be positive reward or negative rewards. MDPs are non-deterministic problems. It means they are stochastic. In order to solve such problems, we can think of Expectimax algorithm. Expectimax compute the best action. How? By considering expected rewards across probabilistic branches. However, Expectimax only tells us what to do in the current state. It does not compute a policy for every state. However, in case of reinforcement learning, we need a complete policy, not just the isolated decision. So using Expectimax algorithm, we can think of our objective in MDP, and what is that? Maximizing the cumulative rewards. To do so, we consider a probabilistic model. The model tells us how we can win. It means maximizing the reward. Is it 100% safe? Absolutely no. The final rewards are not guaranteed at all. This algorithm tells the agent what action to select. It means it can lead you in the maximum possible rewards. And accordingly, we can have an optimal policy. Each MDP state projects an Expectimax like search tree. In each state, we have several choices. We can take an action. The action takes us to the next state. So you can see here we are in S, we take an action, and then we will move here and there based on the action that we take in every state. So let me give you one summary. So far, we understood that MDP's Markov decision process provides a mathematical formulation for reinforcement learning. We have the agent environment loop that describes interaction and continuous feedback. Then we have deterministic and stochastic environment that they require different planning approaches. Then we learn about Bellman equation that give us a recursive framework for computing optimal values. Then we learn about Expectimax that is conceptually useful, but it is insufficient. Why? Because reinforcement learning requires optimal policies over an entire state space, not only a single state decision. So our objective is to find an optimal policy, but we don't know T or R. Just we must try out actions. What is the idea here? We compute all average our time T using complete outcomes. We may have offline mode that we call it as MDP, or we may have online learning that we call it as reinforcement learning. In general, online learning, it means we are doing it as the data or experience comes in. And in case of offline, it means we have a static data set or we have a set of fixed information about the environment. These two are based on T and R. If it is offline, we deal with MDP, Markov Decision Process. Otherwise, it is online and we deal with reinforcement learning. It means reinforcement learning is an MDP, but we don't know T and R. So reinforcement learning is a type of MDP, but T and R are unknown to us. As I said already, we have two main types of reinforcement learning. One is model-based, another one is model-free. Model-based build a model of the environment. It learns at approximate model based on what? Based on experience, and this needs memory a lot. It's kind of memory-intensive learning method. On the other side, we have model-free. This learns a policy without any model. We can think of temporal difference methods, we will study later, and also it requires limited episodic memory. And here we have types of, for example, actor, critic learning, and cue learning. So once again, in the case of model-based reinforcement learning, we attempt to learn the transition function and also reward model of the environment. With this model, the agent can plan ahead using algorithms like value iteration or policy iteration. However, in case of model-free reinforcement learning, we learn value function or action value function directly. We don't have any attempt to estimate the environment's dynamic. These model-free methods are extremely popular. Why? Because in many real-world problems, the transition model is unknown. It is too complex and it is impossible to estimate accurately. In the case of model-based learning, the agent tries to learn an approximation model based on the collected experience that we have. And then if the learned model works well, it can be used to solve for values. In this method, we deal with two steps. One is learn empirical MDP model, and another one is solve the learn MDP. In the first step, the agent tries to learn some models based on experience. In here, the agent considers the outcome of each action in a given state. Whereas we do not have T and R, so we find estimation of T and R that we show them by T hat and R hat. Then we find an estimate of T hat, like T hat is equal to S, A, and S prime. And then we discover each R hat as the S, A, and S prime when we experience S, A, and S prime. Then in here, in the next step, we try to solve the learn MDP value iteration as we did before. Let's see another example here. Suppose we want to find the expected age of students in a given class. There are two possible ways. Either we know the probability of each outcome or we don't know. If we know, it is simple. Just multiply the probability of each one and then sum of them together, right? Very easy. Otherwise, if we don't know the probability, then we need to do some sampling. So the example can be expressed in the form of model-based and model-free. Our goal is to find the expected age of a student in a class. Two ways are there. Either we have a probability like PA or we don't have this PA. If PA is known, so the average is probability of each one multiply the value, PA multiply A, then we can find it. And if we don't have that, we can go for model-based and model-free. The model-based says estimated probability is number of students with age A divided by N, right? And in here, we say that it's equal to 1 by N, sum of all age that we have. In the category of model-free learning, there are two types. One is called as passive and active. Passive reinforcement learning, in here, the agent follows a fixed policy and simply evaluate it. The objective here is to learn the value of the policy. We don't want to improve it. However, in the case of active reinforcement learning, the agent must evaluate and also improve the policy. The agent chooses action. It explores the environment and also it updates the policy based on observed outcomes. Most real reinforcement learning tasks are active learning. We want the agent not only to evaluate, but to discover the optimal policy. So once again, passive, it means the agent policy is fixed, which means it is told what to do. So we have instructor and we tell them what to do. We have a policy like pi, and we learn how good it is. Why we call it passive? Passive in the sense that the agent does not choose action itself. The policy tells what to do. So the agent has to go the way that the environment imposes based on the available policy or pi. However, in case of active, so the agent makes choices what to do because there is no fixed policy that it can act based on that one. The fundamental trade-off is needed. Exploration vs. exploitation. Right? Exploration and exploitation. This is not an offline planning. The agent actually takes action in the world and it tries to find out what happens. So in here we have mutual direction. In passive reinforcement learning, the agent has no control over the policy. It follows the provided policy exactly, and the agent focuses solely on learning the value function. This is useful for policy evaluation problems, but it is insufficient for tasks that require policy optimization. So we have, like, for example, here we have a simplified task that is policy evaluation. The input here is a fixed policy like pi s. We don't know the transition probability, and also we don't know the reward function. The goal here is to learn the state value. In this case, the learner is along for the ride. It has no choice about what action to take and just execute the policy and learn from experience. This is not offline planning. You actually take action in the world. So in the case of passive learning, we need to learn direct evaluation. Direct evaluation is a method that we use for passive reinforcement learning. The idea is here, we run many episodes following the given policy. We compute the total return from each state, then we find the average of their return to estimate the state value. This method is very simple, but it requires full episodes. It means it can be insufficient or expensive. So our goal is to compute values for each state under policy that we have. The idea is very easy. We average together observed sample values and we act according to the policy. Then every time we visit a state, then the agent write down what is the sum of discounted reward returned out to be the average of those samples. So what are advantage and disadvantage of direct evaluation? It's easy to understand. We don't have to have information about T and R, and in direct evaluation, finally we can have the correct average value based on the sample transition. But on the other hand, there are several disadvantages associated with direct evaluation. This direct evaluation based information about state connections. Each state must be learned separately, so it has very high time complexity. Now, we want to estimate the expected return of a particular policy if we don't have access to true MDP models. To do so, we go for simplified Bellman equation to find V for a fixed policy as pi. In each round, we just replace V with one step look ahead layer over V. This approach fully exploits the connection between the states. We need T and R to do it. So in policy evaluation, we compute value function iteratively without waiting for episodes to finish. So in this approach, we use partial returns, dynamic programming updates, best current value estimate, and this is for more efficient and it allows online updating. So in this case, the V of pi k plus 1s is equal to sum of, for all possible states, T of s pi and s prime reward, and this is the discount factor, and we try this one for all possible states. Remember, our main goal here is to improve the V estimation via this equation. We want to improve V estimation based on this equation. For example, how will you evaluate a biased coin, or how you can find average of students in 15 up to 28 years old? To do so, the first idea is to take sample of outcome like S prime by taking an action like the average. So the sample number 1 tell us this one, sample number 2 this one, and up to sample n. Finally, we can calculate value based on 1 by n for each sample that we have calculated here. By iterating this update, the value function converts to the true value of the policy. This is a cornerstone of dynamic programming in reinforcement learning. So the next topic is temporal difference learning. This is one of the most important ideas in reinforcement learning. In here, we try to update values step by step. It does not require full episodes. It blends the strength of Monte Carlo and dynamic programming, and it is the basis of Q-learning and the SARSA algorithm. So we have some of these like samples that we calculate based on this equation. The next topic is active learning. In active learning, the agent must select actions. The agent must explore the environment. The agent must find an optimal policy. So active learning is significantly more complex because the agent must balance between exploration and exploitation. So once again, active learning, in fact, it is the full reinforcement learning. We try to find the optimal policies like value iteration. The agent select an action. We don't know about T, we don't know about R. We take an action at a time and we don't have any policy. The goal here is to learn the optimal policy that is pi star. In this case, the agent makes choices. This is not offline planning. You actually take action in the world and you find out what happens. The main challenge here, as I said, is the balance between exploration and exploitation. Later, we will study Q-learning as one algorithm of active learning. At the end, let me now summarizing everything we have discussed about solving reinforcement learning problems and how the choice of methods depends on what we actually know about the environment. We divide reinforcement learning in two major categories: when MDP is noun and when MDP is unnown. So this is first category and second category. When the MDP is noun, Markov Decision Process, it means we already know the transition function and their reward function. T and R are known to us. This is referred to as an offline solution. We call it as offline solution because all computation can be done without interacting with the real environment. We want to compute value function, we want to compute optimal action value function, and we want to compute optimal policy, right? V star, Q star, and pi star. Or simply, we want to evaluate a fixed policy if we are not optimizing. The techniques we can use here, they are classical dynamic programming methods like value or policy iteration and policy evaluation. Because we know T and R exactly, these algorithms can compute optimal solution mathematically with no exploration required. But the problem is when MDP is unknown, it means T and R are unknown to us. In this case, we must learn from experience, that is reinforcement learning, real reinforcement learning. These split into two major families, model-based and model-free reinforcement learning. So in the case of model-based reinforcement learning, the agent tries to learn an approximate model of the environment. The agent estimates transition probabilities. It estimates reward function, and then it tries to solve approximate MDP using dynamic programming. The goal remains the same. We want to find out V star, Q star, pi star, right? Or we want to evaluate a fixed policy. So we can use different techniques here. We can go for value iteration, we can go for policy iteration on learn MDP model, or we can go for policy evaluation on the learn model. So the key idea here is first learn the model, then plan using the model. And finally, we have model-free reinforcement learning. In model-free reinforcement learning, the agent does not attempt to learn the transition model. Instead, it learns value directly from experience. The goal again here is to find V star, Q star, and pi star, or we want to evaluate a fixed policy like pi. The main techniques here are Q learning. The next lecture, we will study Q learning. In the Q learning, we want to learn the optimal action value function directly without knowing the model. Then we go for temporal difference or value learning. This method updates estimates step by step using partial feedback. So this model-free family is extremely popular because it avoids the complexity of model estimation. So once again, if we know MDP, we solve it offline using dynamic programming. If we don't know FDP, we can either learn a model that is model-based or learn value directly, that is called as model-free. Thank you very much for your attention. Please feel free to ask me your questions and see you in the next lecture.